when I talk about real numbers, if I am talking about real numbers, in the case of real numbers, you give me any two real numbers A and B. The law of trichotomy says that either A will be greater than B, or A will be less than B, or A will be equal to B. Either this will hold, or this will hold, or this will hold. This is what is said by the law of trichotomy. But if I talk about complex numbers, in the very case of complex numbers, what happens is, if you give me any two complex numbers, say a1 plus iota b1 and c1 plus iota d1, or suppose I take a2 plus iota b2, let's just take a plus iota b and c plus iota d. This is one complex number, this is another complex number. If you give me two complex numbers, z1 and z2, I can never ever conclude about whether z1 is greater than z2, z1 is less than z2, z1 is equal to z2. z1 is equal to z2 is a concept which is valid, obviously, but I cannot actually compare two complex numbers. z1 greater than z2, this concept just does not exist. z1 less than z2, this concept just does not exist. One complex number cannot be compared with the other complex number in terms of being greater than or less than that complex number. Why? Because a complex number is made up with the real part and the imaginary part. This is another complex number made up with the real part and the imaginary part. This makes sense. What makes sense? Comparing real numbers makes sense. But comparing complex numbers does not make sense, because these are made up with their real as well as imaginary parts. So, there are two real numbers contributing to the construction of one complex number. This complex number is made up with two real numbers A and B. This complex number is made up with two real numbers C and D. That means you are not comparing right now two real numbers, you are actually comparing four real numbers. Two from here and two from here. How can I say that these set of real numbers are greater than this set of real numbers? How can one set be greater than the other set? This is completely an absurd concept, and that is why one real number can be greater than or less than the other real number. In fact, it always is, or it is equal to. But when I talk about complex numbers, no two complex numbers are ever comparable. You can never ever compare two complex numbers as to one being greater than the other or one being less than the other. It is a completely redundant concept when it comes to the field of, or to the very set of complex numbers. Is it clear? So, this greater than, less than is just restricted to real numbers. It is, the moment you move out of real numbers, you know real numbers is a very big set, but then the extension of real numbers was complex numbers. The moment you move out of the real numbers, the comparison factor gets lost. The comparison factor gets lost. You are not allowed, you are not able to compare any two numbers which are not real in terms of being greater than or less than. The only thing is valid, which is equality. You have learned the concept of two complex numbers are equal when the real parts are equal and imaginary parts are equal. So, equality concept definitely holds, but when I am talking about specific comparison as to one being greater than the other, that concept is lost when you move out of the set of real numbers. The moment you start handling complex numbers, iota, a plus iota b, c plus iota d type of numbers, that means you are no more there in the real number set, the comparison factor gets lost. So, no two complex numbers can ever be compared, but yes, any two real numbers can always be compared by the law of trichotomy. So, when I talk about complex numbers, understand one thing very carefully, I can never compare two complex numbers. No two complex numbers can be compared in terms of greater than or less than. So, what happens is, We know that corresponding to any complex number is a non-negative real number which is its modulus. Of course, if Z1 and Z2 are given to me, I cannot compare Z1 and Z2 like Z1 is greater than Z2 or Z1 is less than Z2. No, I cannot do this. But what I do is, I compute the modulus of Z1, I compute the modulus of Z2. Modulus of Z1 is a non-negative real number, modulus of Z2 is a non-negative real number. I can always compare two real numbers with the law of trichotomy. So, this is definitely going to come out either this way or this way or this way. So, complex numbers cannot be compared, but what can be compared associated to them is their modulus. Because the moment you talk about modulus of a complex number, you enter into the real number set. Because modulus of a complex number is a real number, and I know that real numbers can be compared in terms of greater than or less than or equal to, right? And therefore, comparing complex numbers is not possible, and therefore associated to complex numbers is the concept of modulus, and so we compare the modulus. We cannot compare the complex numbers, but we can compare their modulus, because modulus are real numbers and we can compare the real numbers. So, please keep this concept very nicely in mind, that whenever you have 2 plus 3 iota is greater than 7 plus 9 iota, then this is absurd. This is a completely absurd, redundant, waste statement. This is never possible, and in fact this makes no sense. In what context are you saying that 2 plus 3 iota is greater than 7 plus 9 iota, for example? In what context are you saying? 2 is greater than 7 or 3 is greater than 9? What are you saying? Or 3 is less than 9? 2 is less than 7? What are you saying? In what context can you say that one complex number is greater than the other complex number or less than the other complex number? This is a redundant concept. There is nothing like 2 plus 3 iota is less than 7 plus 9 iota, or 2 plus 5 iota is greater than, say, 6 plus 4 iota. There is no concept like comparison of two complex numbers in terms of greater than or less than. Is it clear? This is a short note you should always keep in mind, that the moment you move out of the set of real numbers, the moment you start handling numbers which are no more real, the concept of comparison gets lost. So, at the cost of increasing the size of real numbers, and extending it to the set of complex numbers, we actually compromise with the comparison factor. Understood? We do extend the set of real numbers when we are able to obtain this large collection of complex numbers which is beyond the set of real numbers, but we compromise with the comparison factor. On one hand, where every real number, whether natural or whether rational, irrational, we are able to compare them. The moment we move out of the real number set, we are not able to compare them. Okay, in order to involve a comparison factor, in the case of complex numbers, we introduce the concept of modulus, so that modulus of a complex number becomes a real number. That is how it is defined, and then we are able to compare the modulus, but not the complex numbers. Okay, coming back to our very concept, which was square roots of a complex number. Square roots of a complex number. I had told you that I will be taking any complex number. Suppose I take this complex number I had taken, and I was telling you that if you have this complex number, that means you are aware about the value of a and b, which is sitting over here, actually making this complex number a plus iota b. Let z equals a plus iota b be any complex number, and let square root of a plus iota b be equal to x plus iota y. Now this x I don't know, this y, as I was saying, I don't know, but a I know and b I know. This is my given complex number. I wish to compute its square roots. So the square root of a complex number will come out to be a complex number, say it is x plus iota y. I told you that square root of a number x is equal to y if and only if y square is x. You know this? Root x is y if and only if y square is x. So root of a plus iota b is x plus iota y. This means what? X plus iota y whole square is a plus iota b. We have already done this. What do you mean by this? This implies x square plus iota square y square plus 2 iota xy is equal to a plus iota b. This means x square minus y square, because iota square is minus 1, plus iota times 2xy is equal to a plus iota b. You can see over here, this is the real part and this is the real part. This is the real part of the left hand side complex number, this is real part of the right hand side complex number. 2xy is the imaginary part and here b is the imaginary part. If two complex numbers are same, that is only possible when the real parts are same and imaginary parts are same. So here if these two complex numbers are same, this implies what? What does this imply? This implies real parts are same. So you have x square minus y square is equal to a, and you also have 2xy is equal to b. I had stopped over here. I told you to mark this as two equations, and with the help of these equations or some other relationship which you can establish, you have to compute the value of x and y. So right now my target is to compute x and y. The moment I get x and y in terms of a and b, my very question will be solved, because a and b I will always be knowing. Find out the square root of 2 plus 3 iota, for example. That means I know a is 2 and b is 3. If I find out x and y in terms of 2 and 3, in terms of a and b, with the help of a and b's value, I will be getting my x and y and hence getting the answer of square roots of under root a plus iota b. So my target is to compute x and y. Now these two relations themselves, in themselves, are not enough to give me the value of x and y. You can try that. Another convenient way, a very convenient approach of doing this is establishing another relationship between x, y, a and b, so that I can use one of these relations and that relations to get the value of x and y. Fine. So as I had given you the hint also, try to create something with the help of x square and y square, so that one relation already we have in terms of x square minus y square. The other relation, if gets converted in terms of x square plus y square, we are going to just use this relation and that relation to get the value of x and y, and it would be very convenient to solve them by elimination method. So what I do is, this is something that should be thought by you on your own. If I take x square plus y square whole square, x square plus y square whole square, this happens to be x square whole square plus y square whole square plus 2x square y square. It's a square plus b square plus 2ab. This becomes x square whole square plus y square whole square. Now 2x square y square can be written as 4x square y square minus 2x square y square, because 4 minus 2 is 2. 4x square y square minus 2x square y square gives you 2x square y square. And now if you focus, this is x square whole square plus y square whole square minus 2x square y square. This is nothing but x square minus y square whole square. A minus b whole square is a square plus b square minus 2ab. So actually I have constructed from x square plus y square whole square something like x square minus y square whole square plus 4x square y square. Now I can write this as x square minus y square whole square plus 2xy whole square. You know that x square minus y square is a and 2xy is b. X square minus y square is a, so x square minus y square whole square is a square. 2xy is b, so 2xy whole square is b square. You have got x square plus y square whole square is a square plus b square. X square plus y square whole square is a square plus b square. This means x square plus y square equals plus minus square root of a square plus b square. But x is a real number, so x square is always non-negative. Y is a real number, square of any real number is always non-negative. Sum of two non-negative terms is always non-negative. That means x square plus y square is a non-negative term. It can never be negative. So it will always be plus over here. X square plus y square can never be minus of root over a square plus b square. It has to be plus of root over a square plus b square only. I know minus cannot prevail over here because left hand side is non-negative, it is equal to the right hand side. So right hand side also cannot be negative, it has to be non-negative. So here what have I got? X square plus y square is root over positive square root of a square plus b square. Now you have a relationship with x square plus y square a and b and here you have x square minus y square. So by using 1 and 3, what do you get? Once you have x square minus y square equals a, and then you have x square plus y square equals root over a square plus b square. So I have written equation 1 and equation 3. I know how to solve this. If I add, what do I get? X square plus x square gives me 2x square. This is 0. This is a plus root over a square plus b square. So you have got your x square. Therefore, x square is a plus root over a square plus b square whole upon 2. Therefore, x is plus minus square root of a plus root over a square plus b square upon 2. Okay, so x we have attained. Similarly, from these two relations itself I can attain y also, and I have these two relations, x square minus y square equals a and x square plus y square equals under root a square plus b square. If I plan to subtract these two, I get x square minus x square cancel, minus y square is minus 2y square equals a minus root over a square plus b square. Clear? This minus, I can take out minus from here, I will be left with, what will I be left with? I will be left with y square is equal to root over a square plus b square minus a, because when you take out minus common you are left with root over a square plus b square minus a. Minus from here and minus from here get cancelled out, you are left with this upon 2 as y square, and therefore y is plus minus square root of under root a square plus b square minus a whole upon 2. First question says find the least positive value of n if 1 plus iota upon 1 minus iota raised to the power n is 1. Now obviously 1 plus iota upon 1 minus iota is representing a complex number with what real part, what imaginary part, we need to decode that, and then we are going to raise it to the power n and find out what is that least value of n for which it gives out 1 as the answer. So if you consider 1 plus iota upon 1 minus iota, clearly in order to decode what is the real and the imaginary part, we are going to multiply and divide by what? 1 plus iota, 1 plus iota. This gives you 1 plus iota whole square whole upon 1 plus iota into 1 minus iota. A plus b, a minus b is a square minus iota square. Minus iota square is minus of minus 1, which is plus 1. So you are left with what? This is what? 1 minus iota square. Iota square is minus 1, so you are left with 1 plus 1. Now this gives you 1 plus iota square plus 2 iota whole upon 2, which is 1 minus 1 plus 2 iota upon 2, because iota square is minus 1. Now in here when I am talking about 1 plus iota square plus 2 iota whole upon 2, because iota square is minus 1, this is what I have got as the expression, and now this turns out to be 2 iota upon 2, which is iota. Eventually what we are getting is that 1 plus iota upon 1 minus iota is coming out to be equal to the complex number iota, which can be written as 0 plus 1 iota. So we have decoded the real and the imaginary part of this complex number, right? And therefore what eventually we have got is that 1 plus iota upon 1 minus iota is actually 0 plus 1 iota. That is iota. Corresponding to iota, I know that iota raised to the power 1 is iota, iota raised to the power 2 is iota square, that is minus 1, iota raised to the power 3 is minus iota, and iota raised to the power 4 is 1. For the first time when iota raised to any natural number as power is giving you 1 is 4. The moment you move to iota raised to the power 5, again it would be iota, iota raised to the power 6 would be again minus 1, iota raised to the power 7 would be minus iota, iota raised to the power 8 would be 1, right? So iota raised to the power 8 would be 1. But the least very natural number, for the first time when iota raised to any power, where that power is a natural number, the least such natural number for which iota raised to that particular natural number as the power is giving you 1 is 4. So, and as 4 is the least natural number, as 4 is the least natural number such that iota, least natural number n such that iota raised to the power n is 1, therefore 1 plus iota upon 1 minus iota raised to the power n is actually iota raised to the power n equals 1 for least n equals 4. The least natural number n for which 1 plus iota upon 1 minus iota raised to the power n is 1 is n equals 4. So, your answer is n equals 4. Next question says that find the modulus and argument of this complex number. Again we have the same complex number, 1 plus iota upon 1 minus iota. I just told you how to decode the real and the imaginary part of 1 plus iota and 1 minus iota. It comes out to be iota. The moment you have the real and the imaginary part of this complex number, say z, I am saying let z be 1 plus iota upon 1 minus iota, which we know is iota, which can be written as 0 plus 1 iota. This implies real part of z is 0, imaginary part of z is 1. Find the modulus and argument. Modulus of z is under root of real part of z whole square plus imaginary part of z whole square, that is under root of 0 square plus 1 square, which is 1. And if I talk about argument of z, we need to first find tan alpha, right? Let alpha be the acute angle for which tan alpha is mod of imaginary part of z upon real part of z. Imaginary part of z is 1, real part of z is 0, so you are getting 1 upon 0, which is infinity. Alpha comes out to be equal to pi by 2. Clearly, what is happening is real part of z is 0 and imaginary part of z is 1, that is positive. This implies z lies on the y-axis, that too on the positive y-axis. You can see 0, 1 are the actual coordinates in the Argand plane. 0, 1, that means what? X coordinate is 0, y coordinate is 1. So, 0, 1 point lies on the y-axis, that too on the positive side of the y-axis, and therefore principal argument of z is pi by 2. So, modulus of z is 1 and argument of z is pi by 2. Let me just show you. This is 0. From here to here, if you measure the distance of 1, this particular point 0, 1 is the point which is actually representing iota, then this particular complex number is actually making 90 degrees with the positive direction of x-axis, and it is 1 unit apart from the origin. So, 1 unit is the modulus and 90 degrees the argument. This is where iota is sitting in the Argand plane. Next I have solve this particular quadratic equation. Pretty simple, we just need to compute the discriminant. Let's compute D. Here if I compare it with ax square plus bx plus c equals 0. So on comparing with ax square plus bx plus c equals 0, we have a equals root 5, b equals 1 and c again equals root 5. Discriminant is equals to b square minus 4ac. B square means 1 square minus 4 into a into c. 1 minus 20, which is minus 19, which is less than 0. Therefore, this quadratic equation is going to have what? Two distinct imaginary roots. Therefore, if I say this is 1, I am going to say 1 has two distinct imaginary roots, alpha and beta, where alpha is minus b, so minus b plus root over b square minus 4ac upon 2a, and beta is minus b minus root over b square minus 4ac upon 2a. This means what? Alpha is minus 1 plus root 19 iota upon 2 root 5, and beta is minus 1 minus root 19 iota upon 2 root 5. These are your given two roots. Next question, if we move on to, we have this particular expression given, and that too an equation in the form of complex number z. We need to show mod z is 1, right? Try to think upon it, how basically this equation can help us to get the very modulus of this z as 1, and then we are going to be right back to the same question. So in here basically the point of this particular equation given in the complex variable z is what? If I say that we have iota z cube plus z square minus z plus iota equals 0. The first thing that you focus upon is I want z cube's coefficient to be 1. I need to remove this iota from picture. So what we do, we divide both sides by iota. Please understand one thing, whenever you divide by iota, you get 1 by iota, multiply and divide by iota, so you get 1 into iota, iota into iota, both these are same. This is iota upon iota square, which is iota upon minus 1, which is minus iota. So please remember, 1 by iota always is equal to minus iota. Fine. Now in here when I divide by iota, I get iota z cube upon iota plus z square upon iota minus z upon iota plus iota upon iota equals 0 upon iota is 0 only. This gives you z cube. 1 upon iota is minus iota. 1 upon iota is minus iota. Right? 1 upon iota is minus iota, minus minus plus iota, and here you get 1. Now what do? You basically manipulate this expression. You write plus 1 as minus iota square. 1 is equal to minus iota square. Iota square is minus 1, minus minus is plus, so minus iota square gives you plus 1. From here you can take out z square common, you are left with z minus iota. And from here you can take out iota common, you are left with z minus iota. So you get z minus iota, and this is z square plus iota equals 0. So here, what is it that you get? Then next is, this implies z minus iota is 0 or z square plus iota is 0. This implies z is iota or z square is minus iota. If z, complex number z is same as the complex number iota, that means their modulus is same. And here these two are same, that means their moduli is same. Right? What is modulus of iota? We just found out in the previous question, it was 1. You can write iota as 0 plus 1 iota, and then modulus would be under root of 0 square plus 1 square, which is 1. From here you know mod of z square is mod z whole square. Mod of minus iota is same as mod iota. You know modulus of z is same as modulus of minus z. So here this is equal to 1. So you are getting mod z is 1. Mod z whole square is 1, that means mod z is 1 because mod z is a non-negative quantity. The only quantity whose square can be 1 is 1 when mod z I know is non-negative. So in both cases mod z is coming out to be 1, and hence we have established that if this equation prevails in the complex variable z, then mod z has to be equal to 1. Next we have find real value of x and y for which this complex number and this complex number are conjugates of each other. Now already the relationship between these two complex numbers is full-fledgedly given to you, right? So you are given that this complex number and this complex number are conjugates. Write it in the mathematical format. This complex number is complex conjugate of this complex number. That means this complex number is this complex number's conjugate, bar. This complex number is this complex number's bar. That means when you take this complex number's bar, you get this complex number. That is what is the meaning of being conjugate. That means minus 3 plus iota times x square y is equal to, what do you do when you take bar? You actually just replace the coefficient of iota by minus of that coefficient. So x square plus y, real part remains unaltered, 4 is the coefficient of iota, you replace it by minus 4. That is what it is. Now these are two complex numbers which are equal, that means their real parts are same and imaginary parts are same. Real part of this is minus 3, this is x square plus y, and imaginary parts are also same, x square y equals minus 4. Say this is 1, this is 2. This is also holding and this is also holding, both are holding. From 2, we have that x square is equals to, or rather than that I should write y is equals to minus 4 by x square. Putting 3 in 1, we get, if you put this 3 in 1, you get minus 3 equals x square plus y is what? Minus 4 by x square. So you have minus 3 is equals to x square plus minus 4 by x square. This gives you minus 3 equals x to the power 4 minus 4 whole by x square, which implies minus 3x square equals x to the power 4 minus 4, which implies x to the power 4 plus 3x square minus 4 equals 0. If you for the time being write x square as w, you actually get w square plus 3w minus 4 equals 0. Now it is in the form of quadratic equation, you know how to solve it. Try to break the middle term. You have minus plus 4w minus w minus 4 equals 0. This gives you w plus 4 minus 1, w plus 4. So you have got w plus 4 into w minus 1 equals 0. W is x square plus 4 into x square minus 1 is 0. This implies x square plus 4 is 0 or x square minus 1 is 0. Let me rub this. Okay. First of all, please understand, look at the question again. I want real values of x and y. Complex numbers or imaginary values of x and y are not permitted in this question. So this implies x square plus 4 is 0 or x square minus 1 is 0. But I know that x square plus 4 equals 0 means x square equals minus 4. That means x equals under root of minus 4. That means what? 2 iota. This is going to give me imaginary values of x for which x square plus 4 is 0. There is no real number x which is satisfying x square plus 4 equals 0. But there does not exist any x belonging in R such that x square plus 4 is 0. Therefore, x square minus 1 only can be 0 to make this equation equal to 0. This cannot be 0 for any real x. That means only this has to be 0 so that the product comes out to be 0. That means x square is 1, which means x equals plus minus 1. If x is plus minus 1, y is what? The moment I am saying x is 1, for x equals 1, y is what? If x is 1, 1 square is 1, y is minus 4. And if x is minus 1, if x is minus 1, suppose here you put x is minus 1, this is again 1, so you get minus 3 minus 1, again y is minus 4. So the real values of x and y, which are basically going to make these two complex numbers conjugates of each other, is x1 y minus 4 or x minus 1 y minus 4. These are the values. Next question we have, find the conjugate of this given complex number. Now, please understand what was the drill to find the conjugate of any complex number. Let us write this complex number down. And here when you have this complex number with you, it is 3 minus 2 iota, 2 plus 3 iota, whole upon 1 plus 2 iota and 2 minus iota. Try to simplify. 3 into 2, 6 plus 9 iota minus 4 iota minus 6 iota square, whole upon 2 minus iota plus 4 iota minus 4 iota square. This means plus 6 and this means plus 4. Iota square is minus 1. 6 plus 9 iota minus 4 iota minus 6 iota square. This is 2 minus iota plus 4 iota minus, this is minus, plus 2 iota into minus iota means minus 2 iota square. So, plus 2, right, because 2 iota into iota is 2 iota square, which is minus 2 into minus is plus 2. 6 plus 6 gives you 12. 9 iota minus 4 iota is 5 iota. Whole upon 2 plus 2 is 4 plus 3 iota. 4 iota minus iota is 3 iota. Now what I do is, in order to find the conjugate, I multiply and divide by 4 minus 3 iota and here also 4 minus 3 iota. What do you get? 12 into 4 is 48 minus 36 iota plus 20 iota minus 15 iota square. A plus b, a minus b is a square minus b square. 48 plus 15 gives you 63 minus 16 iota upon 25. And this is what is the required conjugate of your given complex number. Conjugate of this complex number is equal to this complex number. Clear? Easy enough? Next we have solve this quadratic equation using the general expression for the roots of a quadratic equation. Okay, so here we just need to directly use our formula to evaluate the roots. This is your a, minus 4 is your b and 3 is your c. Ax square plus bx plus c, discriminant is b square minus 4 into a into c. That is, d is what? 16 minus 4 into 2, 8, 8 into 3 is 24, which gives you minus 18. Isn't it? Because you have, this is minus 8. Clear?
If discriminant is -8, this is again less than 0. If I say this equation is equation number 1, in this situation, one has two distinct imaginary roots. There will be no real roots prevailing. Obviously, there will be imaginary roots, and that too two and that too distinct. Clear? Say alpha and beta, where alpha is minus b plus root over b square minus 4ac upon 2a, and beta is minus b minus root over b square minus 4ac upon 2 into a. This gives you 4 plus 2 root 2 iota, because root 8 is 2 root 2 and root minus 1 is iota, whole upon 4, and beta is 4 minus 2 root 2 iota upon 4. Obviously 2 can come out common. What will you be left with? If 2 comes out common from the numerator, what will you be left with? 2 comes out common, you are left with 2 plus root 2 iota whole upon 2, and beta is 2 minus root 2 iota whole upon 2. Is it clear? And this gives you 2 upon 2 is 1, root 2 upon 2 is 1 by root 2. This is alpha, and again 2 upon 2 is 1 minus 1 by root 2 iota. These are your two most simplified form of the roots of this given quadratic equation. Next we have find the square root of iota. Now the drill that is used to find the square root of any complex number should be at your fingertips, and then you will be able to decode the very square root of iota within no time. Let's do that. Let z be equal to the complex number iota, which can be written like this. Fine. Now in here, if z is equal to iota, I am interested in root iota, square root of iota. Suppose this is equal to x plus iota y. So iota will be equal to x plus iota y whole square, which is a square plus b square plus 2 iota xy. This is the real part and 2xy is the imaginary part. If iota is equals to x square minus y square plus 2 iota xy, that means real part is equal to the real part, imaginary part equals to the imaginary part. Real part of iota is 0. So 0 is equals to x square minus y square, and 1 is equals to 2xy. After this, what was the step? We always assumed one thing, that x square plus y square whole square, if you simplify, you get x square minus y square whole square plus 2xy whole square. Simply x square minus y square whole square, that means 0 whole square, which is 0. 2xy is 1, 1 whole square is 1. You are getting x square plus y square whole square is 1. That means x square plus y square is 1 only. It cannot be minus 1. Can it be minus 1? X square plus y square whole square is 1. That means the next step you would say x square plus y square equals plus minus 1, but it cannot be plus or it cannot be minus 1, because x square is non-negative, y square is non-negative, sum of two non-negative terms is non-negative. We have got x square minus y square is 0, and we have got x square plus y square is 1. If you solve these two equations, solving star and double star, x square minus y square is 0, x square plus y square is 1, 2x square equals 1, x square is 1 by 2, which implies x is plus minus 1 by root 2. If x square is 1 by 2, y square is 1 minus 1 by 2, which is again 1 by 2, which implies y is again plus minus 1 by root 2. But we have that 2xy is equal to 1. For 2 into x into y to give you 1, either both x and y should be positive, so that 2 into x into y is positive, or both x and y should be negative, so that x into y is again positive, so 2 into x into y is positive. If one of the x and y is positive, other is negative, that means x into y will be negative. 2 into x into y will be negative, but 1 is positive. So how can a positive and a negative quantity be equal? Therefore, for 2xy to be equal to a positive quantity, both x and y should be positive or both x and y should be negative. But 2xy is equal to 1. This implies x and y are of the same sign. Therefore, root iota, either it is equal to 1 by root 2 plus iota times 1 by root 2, x plus iota y, where x is positive, y is positive, or it is minus 1 by root 2 plus iota times minus 1 by root 2. Both should be either negative or both should be positive. They actually should be of the same sign because 2xy is 1.